Okay, so we'll try during this session and the next one. I think it's planned on the next week, if I'm not wrong. So we'll try to cover the CFD, the flow simulation solution we have. So we will focus on the desktop solution. You may know that as well. We have a platform solution. Anyway. Let's start the SolidWorks Flow Simulation. Today, I would like to present, let's say, some foundation on the CFD, and depending on the time, I think today we'll be able to see some example. And of course, you know, we may answer to your question, take the time to look the details, okay? And I hope that the next session we may cover more example and of course answer to your question. So what's the fluid flow simulation ACAS CFD? Okay. It's the computational fluid dynamic. Okay, it simulates the real life of fluid flow and heat transfer problems. Okay, so and it helps engineer when they are designing product involved with flow, gas or liquid, and as well simultaneously with heat transfer and forces. So the CFD simulation can help us, okay? And we can take benefit from this technology. So we may analyze pressure, velocity, as well thermal temperatures around electronic component, for example. We may analyze the turbulence and more, okay? So the goal of, the benefits of this product, it helps you to make a decision on your design. And the question, does it meet the functional requirements I have with a given product, okay? So what is fluid flow? So, if we think about, smoke from chimney, waves. We can see here a plane crossing air or cloud and so on, okay? But not only, we'll see later some additional example, okay? So the most of the simulation products use a method named Navier-Stokes, okay, which consider the fluid as a continuum, okay, and use a macroscopic description, okay. So again, we are using, even in flow simulation or in a flow analysis, we try to solve a mechanical equation that you know, okay. As we can say that here we have we involve the mass, we involve the acceleration, okay, and here we have all the forces, okay. So, and if we look to the detail here, we try to follow the change in the velocity, over time, okay, and the speed and direction which the fluid is moving. And on the right term, okay, we take into account pressure effect, okay, force from pressure, and as well when the gravity is significant, gravity effects if gravity effect is significant, if we take into account, the gravity with the mass, okay? And in addition, we have to add internal forces which are driven by internal stress, okay? For example, viscous effect, where we have shear rate and so on. We should take into account this. So the fluid dynamics is based on the known equation that you use for structural as well, okay? The sum of forces equal to the acceleration. However, for the fluid, the governing equation are not so simple, okay? Very complex. So just here, give you some reference from two researchers like Navier and Stokes. This is why we are naming the type of equation we have to solve, Navier-Stokes equations, okay? Where we have to deal with conservation of mass, conservation of momentum, conservation of energy to solve the equation, okay? And we may apply what we are naming Eulerian or Lagrangian approach, okay? For a small control volume, okay? So the Eulerian approach is around a fixed control volume, okay? What we name spatially fixed volume element. And the Lagrangian approach is to follow the motion of an element, a fluid element, okay, which moving, okay? So it's good to know, again, you don't need to deal with this equation in details. I said that, what I have presented right now is good to know. You don't need to deal with a complex equation manually or something like this, but at least you have an idea what is behind the scene when you have to use a flow simulation product, okay? So the type of fluids we may analyze are mainly liquid and gases or both. And as we told, the fluid is considered as a continuum, which is a macroscopic description. And just to remind, CFD means computational fluid dynamic, which is, let's say, a numerical method to approximate the solution and predict, let's say, the motion of fluids, okay? And depending of the, let's say, the way we discretize the space and the time, we may get a good approximation with a good accuracy, okay? So the equation we talk about, okay, are known. We may write them very accurately, but there is no analytic solution because we are dealing with the complex, we'll see in the next slide, complex partial derivative equation, okay, that we cannot solve by an analytic method, okay? So as I told you, the solution of the governing differential or integral differential equation is approximated by discretization of space and time. Means, discretization of space, if you are familiar with structural analysis, you have to mesh the part. Here as well, we have to mesh the fluid domain, okay? This is the space, the discretization of the space. And of course, we have to discrete the time because we have to find the solution step by step. We cannot find in one time step the solution. So that we have to deal, whatever it is, a transient or it is a steady state analysis, we have to play with time step that the solver will use automatically, of course. So let's now see what is SolidWorks Flow Simulation as we talk in general, okay? So SolidWorks Flow Simulation is a general purpose product for fluid flow and heat transfer, okay, which is integrated with SolidWorks. That is very important advantage, okay? It's powerful 3D design simulation tool. We'll see in some example. It brings fluid flow analysis coupled with the heat transfer simulation. Means if the heat transfer has to be solved, we can do it at the same time. Means the fluid affect the heat transfer and inversely, okay, at the same time. And we enable what we are naming true concurrent engineering. So here's some example: internal and external flow. We may deal with laminar, turbulent, and transient flow. We may deal with rotating like pumps. The fluid can be incompressible or compressible. And we may deal with Newtonian and non-Newtonian like, fluid and other. And as well, we may deal with heat transfer simulation, like you can see for electronic cooling or a heat exchanger, whatever, we can simulate the fluid flow and the heat transfer simultaneously. Now, I think you know this type of slide that we use with SolidWorks product. Okay, as you know, in the past, we have the mechanical engineer designing the part, and we have the CFD specialist. Okay, which are two different persons, and at a given time, this guy has to import this part and deal with the simulation, pre-post, solving, and post results. Okay, which takes time. Okay, and is not associative. Each time there is a change, he has to restart from scratch and restart a new study. So this method is 20, 30 years ago. Today, we have to deal with what we are naming concurrent engineering. Concurrent CFD means while you are progressing in the design, you can do some simulation, take decision to change your design and go further. This is why, if we start early in the process, it's available for any simulation, of course, okay? And as well for CFD, CFD is very heavy for analysis. I mean, in question of complexity, question of CPU time, resource, okay? So the best way is to start very early to not, waste time back to the process, to the design process, and so on. Another advantage of SolidWorks Flow Simulation, it's not the CFD for specialists only, okay? It can be used by designer. So you don't need, the advantage of SolidWorks Flow Simulation is fully embedded inside SolidWorks. So you never need to change, export, import, okay? And you may switch at any time between the SolidWorks design tree and the flow simulation UI, okay? It's very easy to set up the model, we'll see later, easy to use, and does not require in-depth CFD algorithm knowledge. What I have presented in the beginning is nice to know, okay? It's good to know. At least you can have an idea about what we are solving, but you don't need to write equation or to deal with an analytic solution and so on, okay? And you'll see in the example, it's very easy and powerful for the post-processing tool So this is why we can see it's not for specialists, okay? And it's a unique combination of technologies which enables this, okay? The fact it is embedded with SolidWorks, we'll see we have automatic boundary Cartesian mesh. The mesh is very easy to set. Automatically take into account the turbulence model so that the user doesn't need to select something. Boundary layers are automatically calculated. As well, there are some tools to get a good convergence, and you may deal with what if analysis, and you'll see it's very intuitive interface. This combination make the tool concurrent engineering for CFD. So, as I told you, direct use of SolidWorks 3D geometry. So, we don't need to import or to deal with such operation. The fluid domain is automatically recognized. Okay, of course, we need to help the software to say, I want to have internal, external, and so on. We'll see what we have to do for this. You don't need to go and back with a CAD package and so on. And a very important thing that you have a full associativity with the design. When it comes to a design change, you don't need to restart from scratch your simulation. Benefits: no translation step, no complex definition, design on CFD, model stay synchronized, and all resynchronization effort and error are reduced, and shortens learning cycle. You'll see when I will present you, and and maybe you can use the provided tutorial for this if you are able to install Flow Simulation. So I'm going fast in each. I mean, we said previously that we have a set of technologies which enable the product to be a concurrent CFD tool. But here is just to give you an idea how the mesh is automatically taken into account the different parts. As you can see here, when you have some details, the mesh is refined around. Sorry. And when you see here, as you can see here, a very complex shape, okay? We have some tools to refine the mesh in the needed regions, okay? But all these could be done in a smart way and automatically. As I told you, it's very easy to deal what-if analysis. I mean, you want to change a design, okay? You do a simulation with your initial design parameter, and then you change your design, you do another, etc. You'll be able to compare, okay? And you may deal with what we are naming what-if analysis. It's, let's say, a semi-automatic optimization, okay? Because the users select different parameters and compare the results. So it's very easy to deal. Once you have one analysis, you can set in an easy way the what-if analysis. Okay. Convergence. Most of the CFD tools need to converge. To reach the solution. Okay. And here, the user can follow up some values that he needs for the convergence. Okay. So, and of course, there are some internal goals to converge the solution. But in addition, the user can follow up, like you can see in the screen. You can see some curves representing value and so on. For the turbulence model, the user doesn't need to select which model. The flow simulation product has one turbulence model adapted to the technology. Okay, so first it is automatically set, and you don't need to have specific mesh for this compared to some other tools when you need to have boundary layer meshed accurately to get accuracy with turbulence. Okay. And of course, when it comes to simulate a fluid flow, it is important to have or to catch the behavior on the wall, as there is the turbulence effect. Is there some roughness and so on? So it's very important to have accuracy on this because it drives the pressure drop, it drives the flow, it drives the velocity profile and so on. Okay, again, it is automatically modified by the software. And preparing, when you start the simulation, you have a wizard. Okay, so I'm sorry. The wizard will help you to start your analysis by selecting, some parameters. Do you want to deal with just field flow? Is there any heat transfer, conduction, and so on? Okay, so the interface is very easy to use, and it eliminates the expertise, the CFD expertise for the setup. Okay. So more or less, we have covered in some slide the technologies behind this product. Okay, and let me present you some typical application. It's a non-exhaustive list, of course. We talk about pumps. We may see a valve example here, rotating system, and so on. As you can see here, some example. For the valve extrusion process, we can simulate the flow inside the die, jet pump, filter, pump, fan curves, and so on. Heat exchanger, for example, as you can see in this example, it could be a heat exchange between two fluids. Electronics cooling, injection molding device cooling, and so on. Okay, medical application. You can see here that, again, it's a non-exhaustive list. Okay. We can deal, even if it is not the specific tool for this, we can deal with aerodynamic. Okay. We can predict cavitation. We can predict noise level. We can deal with intake and exhaust manifold, automotive engine in cylinder, and so on. Okay, so some problem could be complex, but we can simplify and get some trends with which are coherent. As well, we can for mixing process, could be for air conditioning, spray, rubber co-extrusion, cleansing process, and bathroom mixer. You can see that, we are not, we don't have a limit in a given industry, but of course, we may have some very complex problem that we cannot solve in any case, okay? Because I mean, there are some physics which are not easy to simulate, okay? Explosion, chemical reactions, and so on. So as I told you, we are able to extract, some values like, drag forces, like, the effect on winds on building, and so on. Okay. So these slides, these picture give you an idea about the type of problem we can solve. So first of all, for flow simulation, first of all, you need a SolidWorks license, okay? And in addition to this, flow simulation is an add-ins. You may, when it is installed, okay, you can see here the list of additional product, and flow simulation is there, okay? So you need to enable the add-ins to access to the fluid flow simulation, okay? So I don't know which type of license you have, but again, you need a SolidWorks CAD license, whatever it is standard or professional or premium, okay? Doesn't matter. And you need to have flow simulation added and enabled through and you need a specific license, of course. So here, I'm going to start with this valve, okay? If I do a section here, when the valve is open, okay, we may get fluid flow crossing this valve, okay. I would like, for example, to calculate the pressure drop with the, for example, water flow, okay. To do this, and of course, I can play with different angle of the valve, because if I go to the assembly here, we may see where it is exactly. There are some angles, maybe on the board, if I'm not wrong. So we'll see this later, but we may play with the opening here. Sorry, maybe directly from the mate group. Okay, you have an angle here you can play with to test different value of this angle. Okay, we are not there for the moment. Let's see. The valve is fully open. Not exactly, there is an angle, and I would like to see how the fluid, what is the fluid flow behavior inside this. So first of all, we should consider it is internal flow. Okay, I would like to see only, for example, the water crossing from inlet to outlet, okay, and would like to get pressure drop, velocity profile, and so on, okay. For this, we need to deal with the setup. And as you can see, when flow simulation is installed and enabled, you have here the command manager for flow simulation, like you have for simulation and so on, okay? So once it is enabled, I can use the wizard. Like I told you, the wizard, let's say you may give a project name, okay? Some comments if you need. I can use the current configuration, but flow simulation is able to deal with any configuration. You may select if you want to select, or create a new one if needed. Okay, so from select, I mean, you can select for, this one, if exists, of course. Let's use the current. And go to the next. Okay, so here you have to deal with the units. Okay, do you want to use, I don't know, British units, SI units? Okay, it will not change the results, of course, but help you to get the value in the unit system you want. And even if I have selected this, I can say, okay, I would like to deal with SI system, but for example, for temperature, if I have to use temperature, I would like to use Celsius and some other values, okay? For example, for load, I would like to have what it is, flow rate, the mass flow rate. I can select, from a given list, but you can have your own list. Something like, let's say, whatever. I mean, could be ones, could be, I mean, select what you are comfortable with, okay? As well, for the volume flow rate, it's, I mean, it's usual to deal with, for example, liter per second or liter per minute, for example, okay? So I'm using a SI system with a customized value I can use, okay? And it stay consistent, no worries. The solver will get the units in the right system. It's not your problem, okay? Then I can select what type of physics. So could be just fluid flow, could be fluid flow combined with conduction. Do I have to deal with transient? And they say just check time dependent. Do I have to select gravity or not? Okay, so we can say that if the speed, or if there is not, I mean, a large height of water, you can ignore the gravity. Okay, like here, I don't think the gravity will affect the results. And like we saw in the slide, we may deal with rotation and free surface if needed. Free surface can, you can have liquid, gas, okay, and see, the free surface between the two fluids. Here, by default is external, but I would like to deal with internal. Okay, for the moment, let's ignore the other. We'll see these details maybe next example. And what type of fluid here should be gas or liquid? So we are going to use, here we have an engineering database where you have this list, okay? For liquid or for gases, you have air, blah, blah, blah. Let's select liquid, water, add it. So I will deal only with one material, okay? And go to the next. You can select by default many things, except when you have progressed and if you have expertise in domain, you may set some advanced features, okay? And then the last parameters are the initial condition, and by default, it's good enough. You may remark that as I have changed the temperature from Kelvin to Celsius, now it display temperature in Celsius, okay? And so on. Okay, interesting question. First, it creates a domain surrounding the fluid domain, in fact, okay? But here, the fluid domain is open. And as you can see, there is a message that the fluid domain recognition has failed because the model is not watertight, which is true, okay? Because you have one opening there and one opening there. For fluid simulation, we need to have a closed volume, okay? And I say, yes, I would like to close it. And automatically I can create what we are naming leads, okay, leads. Just select here planar face and it other leads on the side. I can do the same here and it's done. And now it will adapt the new fluid domain. So let me remind, we want to deal with internal flow, okay? No conduction in solids. This is why we have here displayed the boundary of the fluid domain, okay? If I look, if I project, for example, here, you can see the limitation of the fluid domain is on the internal face of the lead I created, okay? By the way, there is an automatic leads creation. You can do it manually as well. Just create, an extrusion to, to fill the, the space here, and that's it. Okay. So this is, let's say, I have now defined the global settings, okay, for this analysis. Okay. What's the next step? Okay. Keep in mind that at any time I can back to the domain, the computational domain, modify something if needed, but of course I can hide it. Okay. Okay. Now we need maybe to deal with some conditions. Okay. To solve a fluid problem, I need some parameters like, which type of fluid, is it internal, is it external? And of course, I need some conditions, okay? This condition could be something at inlet and something at the outlet, okay? So, for example, and I'm going to go to boundary condition, okay? I would like to define a mass flow or a volume flow, okay, as an inlet, okay? Could be velocity or could be outlet mass flow, volume flow, or velocity, of course. So we may switch later. I need to select the internal phase. So there is two methods. So here I can say, yeah, I don't want to select the external phase, which is not in contact with the fluid. I can select other. It will propose me some other option. This one is on the right side, okay? And then I can say, okay, it could be a mass flow or a volume flow, something like, and you remember I modified the default SI units to liter per second instead of cubic meter per second. So, and I can say, for example, 10 liter per minute. It's small, but it's just an. And let's stay simple for the moment, okay? I validate. So here, it used the type of condition you selected, inlet volume flow. Number one, you can have, and you can see the symbol so that you know it is from the external to the internal. So it is in the right side. At least you can check it is not on the wrong direction. And for the other lead internal face, I would like to create, to set a pressure condition, which is, if you are familiar with structural, okay, you cannot have the same type of condition on both sides, okay? If I set flow here or velocity, I cannot set flow here because here I have only one inlet, one outlet. Means the flow rate or the velocity will be at this phase will be calculated by the solver. Okay, cannot impose it. Now we may combine flow rate or velocity by pressure as a complement boundary condition. So I'm going to select in another way. It depends on the complexity of your geometry. Just I can start with a section view. Then I'm able to select this face, the internal face. Okay, just to use another method. And up to you to, once selected, if I go to insert condition, it automatically, use the last selection. And we can say here, the type is pressure. Okay, and if it is directly on the environment, so let's use environment pressure. And let's say now the problem is well defined. Okay, I have enough condition to solve this problem. So sometimes you need to save, because as well the settings are saved with the SolidWorks file, so that if you want to share your settings, just send the SolidWorks file. The flow simulation settings are saved inside the SolidWorks file. Okay, next step. Why I have to, let's say, why I have to solve this? Maybe I need something. Okay, usually we can be interested by the pressure drop between the inlet and the outlet. Okay, and we have what we are naming a notion of goal. Okay, for example, as the inlet, and I just select the inlet here, I go to the goal and insert a surface goal. Why surface? Because I have defined this condition on the surface. Automatically it keeps the selection, okay? And then I can define some goals. Goals will help you for, of course, for the convergence, and as well to get the value you need. Maybe you just need this, okay? And even manually, you cannot get the pressure drop just with an analytic solution, because the domain, the fluid domain is too much complex. Let's say I would like to see the static pressure at the inlet, okay? And save. We may add some other, but let's stay simple for the first case. And then maybe you can say here, you can modify, sorry, the name here. Let's say inlet pressure. It's a static pressure, of course. And to calculate the pressure drop, I need to calculate the difference between the inlet and the outlet pressure. The outlet pressure is defined, okay? So I can create what we are naming an equation, insert equation, okay? So first of all, I would like to take this one, okay? And you can see I have an operator here. And I would like to create this operation, inlet pressure minus outlet pressure. The outlet pressure, I can key in the value, but maybe I can use this one and select this one, and automatically it use the default environment pressure, okay, so that I don't need to unvalidate. And I can say this equation, I would like to name it, oh, sorry, or delta P. So let's say here I have enough condition and I'm interested by the pressure drop. Okay, we can stay simple. Now it comes to deal with the mesh. Okay, now if I'm not an expert, okay, I can use automatic way. You have a cursor here. This is the level of the accuracy you can get. So let's use a medium, more or less. Okay, there is no, let's say it should be enough. And my geometry has not too much complex features, so I don't need to go through some additional detail. But as a first example, let's just use, I just modified the level. I'm ready, let's say, to run. Now, at any time, you can use the feature from the tree, or you can use from the command manager that you can see here. Okay. And as you use run, the run will mesh and then solve. Okay. On this computer, it will use all the cores present in this computer. And at the end, after finishing the calculation, it will load the results. So you can deal with this parameter. Let's go to run. So it opens. Okay, it opens a monitor and it starts the simulation. I'm going to make it finished. Sorry, let me redo it because it went. Calculation, stop. No, not stop, suspend, sorry. Okay, let me close this. So by default, it used the latest, which maybe is not appropriate for the moment. I would like to start from scratch. Okay. So you have this table, this monitor, which help you to follow, let's say, the calculation, to see the progress. Okay. It's another window. At any time, you can back to your SolidWorks, do some other thing. Of course, do not modify the geometry. Let me close the previous one. And keep this one as is, okay? So you have some info here, okay? You can get some warning and you may follow your calculation. For example, you have defined some goals. I can follow the pressure drop and see if it converges or not. And at any time, I can get some section plot, okay? Is plane one good or not? Plane one, and you can see in blue, this is the plane one, and in green, the position of the section plan that you can move if needed. And what I want to see, for example, pressure, or let's say velocity, and you have a section of this. Now, if I continue, because it went too fast, it updates at each iteration the results, okay? And once finished, as you can see, you get solver finished. And as you can see, it's flat here for the value you are looking for. whatever it is, the inlet pressure, sorry, and the pressure drop. The pressure drop is in green here and in red. And you have here the velocity contours. Okay, you can have some other, can have additional section, to follow your solution. Okay, let me close this. Results are loaded like we set in the solver dialog box. Okay, and now we can display our results. First, we may have some cut plots. And cut plots, very easy to manage. It can be on the plane, on the different plane, can be there or there, okay? And once selected, of course, you can move, automatically, if I can catch it. Oh, some graphic. Let me first display, and then if you want to move it, it should move. I'm not catching the right thing. I should catch this one. And as you can see, you can move on both direction. Okay. So let's put it on the default position. Okay. And the type of contour here, it show me the pressure contour. Okay. And as you can see, just to not confuse, this is the inlet on the right, on the left, and the outlet, sorry, the inlet on the left and the outlet on the right. Okay, let's stay like this. As you can see, the pressure is higher at the inlet, which is normal. Okay, the flow goes from higher pressure to the lower pressure. Okay, I can combine. As you can see, it's very easy, just edit. And what do you want to see? For example, I can combine with vectors so that you have an idea about the flow. So very basic, but I have result in any point of the space. That's something I cannot get from analytic solution, if exist, if any. Okay, you may deal with analytic solution when you have a pipe, a straight pipe, and you can use some formula for this. Okay, but when you have, even if this model is simple, we have a complex. We have a complex, more or less, fluid domain to be solved manually. Whatever, I can, of course, switch for the contour to velocity. And at any time, if I need, you can have some sensor here. You can probe and keep it to compare. And then you have here the different values of the velocity, starting here with 0.6 millimeter. And we have some acceleration inside because we have less space here because the diameter is lower than this one, and so on, which is normal. And once we are outside, it decreased to the lower velocity. Okay, so just to give you an idea how to deal with a simulation. It's a simple case, and we saw how we did it. Okay, and remember, we have defined two goals. One of them is the pressure drop. Could be, let's say, the most important value you are looking for. Okay, you can select it here in the goal plots. Okay, and show the value. So for such case, okay, I have an averaged value of 3,500, something like that, Pascal, okay? And I can look to the mean and max and you know, the delta during the convergence, okay? And at any time, I can look to the convergence curve that we saw during the, you know, the calculation, okay? So, of course, as well, you may, as I told you, and you remember in the slides, very easy to use, very powerful, etc., etc. And for example, here in the post results, you know, you don't need to, it's very intuitive. What do you want to get? Okay, just go to the menu and select it. As well, for example, we played with the section view. I can animate this so that it go from the left to the side, and you can see all the section playing, okay, one by one during the animation. What I can get, of course, I can as well look to the trajectories. Let me hide this one. Let me hide, delete all, okay. Flow trajectory. So I would like to catch some particle at the inlet. So I go to this one, use right button on this, automatically selected. Otherwise, you have to select the face, okay? So as it is already selected, it's easy to, and for example, I would like to have lines with arrows, for example, showing the velocity. I can see that. Now you can have some spheres inside, and of course you can increase the number, not too much if you have very complex, and of course, once you have this, so the color is the velocity, okay? And to understand the fluid flow, I think there is nothing better than the animation of this. So it's very easy to understand. Yes, okay, it starts with more or less uniform, and then because I have a smaller diameter, higher, gradient, and so on, and you can see here, you know, the particle do not go straightly from A to Z, okay? Due to this restriction, of course. So, more or less, that's what we are needing. You know, we may stop there for this first example and see more details. But I would like as well to see, for example, we can get some XY plot, okay? And for this, you may select a sketch like we have here. And you can see, I don't know, the pressure and the velocity among this curve. And if you go to show, you have this, okay? If you want to get the profile of the velocity of the diameter, just create the right sketch and you can get these. And of course, what you can see here, you can export to Excel where you have the velocity, the pressure, and as well all the data if you need to create something with these values, okay? And of course, you may create a report. So I'm not going to through this, but you know, report is very, you know, you can create the animation inside, all the things you want. So you may play with this, but there is a possibility to create a report.
I would like to mention something that in the installation, you'll find some examples. Okay, today we saw the a part of the ball valve. Okay, and you can see here it covers the general purpose of a valve, the conjugate heat transfer, the porous media, and so on. Okay, and of course you have in the tutorial the geometry exists. Just use the right geometry, and you can follow step by step what we saw today. Okay, the general settings, the project, and so on. What we saw as initial step today. Okay, and you can follow this step by step if you want to play with the. So it comes with the installation. Okay, and once you get some, let's say, some experience on the product, okay, you can look to the validation case, okay, which are described, of course, here. More or less, these are academic cases where we know the result through an analytic method or something like this, and we show how we can validate our product using these model. So all the geometry, of course, as well are provided. Okay, again, simple geometry, more or less academic examples, but at least you know how to validate a given. Of course, I'm able to share all these documents, the tutorial, the validation, and the examples. I will see with Aliga how to share this. Okay, and as well we have more advanced document like what we are naming technical references. Okay, technical references, will give you the details of the equation if you need to understand something as well, the type of turbulence, boundary layer, mass, and so on. Okay, it's nice to read, but not necessary to use the product again. Okay, so these are the document you can get. Let's back to the, we solved this problem in a very easy way without looking what is behind the scene. Okay, why we need to do this? There is two things. When you are early in the design process, what do you need? You need some trends. Okay, you need some trends, and you don't need accuracy, so that you can use the thing by default. I have not, you remark that I have not displayed the mesh. Okay, there is a mesh behind this. Okay, and the type of mesh, let me unload the results and stay with this. First, if you remember, we just used the global mesh with a given level, and that's it. Okay, so I would like to show you the basic mesh. As you can see inside the fluid domain, this is the basic mesh. Okay, the flow simulation mesh is what we are naming Cartesian mesh. Okay, and it is not a body fitted mesh like we use for some other application. Okay, means somewhere, let me maybe use one of the projection. If we look to some details, you can see here there is a cell which is partially in the fluid and partially in the solid. Okay, and when I plot the results, I will see only the fluid cells. Means the method used here is, how to say, Cartesian mesh with what we are naming cut cells, because some cells has to be cut, because when they are partial, it uses only the fluid volume. If we look to the results, let me maybe make it simple. Hide the vector and show the mesh. This is the fluid domain mesh, okay? And as you can see, and it was done automatically. There is behind I mean, in the measure intelligence, okay, it detect the solid features, okay, cut the cells following the shape of the solids surrounding the fluid, okay. Okay, and you have sometimes what we are naming partial shells, like these, like this one, and all these as well are partial cells, okay. But it is not the user problem. The solver will do the job, okay, and take into account only the part of the partial cells which concern the fluid. When it comes to deal with thermal in solid, of course, it will consider the complement part of the volume which is in the solid, okay? Now, is my mesh accurate enough? Okay. I think, for example, when you look to this, maybe we can have a better mesh around this sharp area. Okay, in section it is sharp. In fact, it's not sharp. But there is maybe something to do there. Okay, how to do it? And at the end, again, if I am in the design process, early in the process, I don't need to do this. Okay, the automatic mesh is good enough. Now, if I want to validate, let's say it is my final design, and before manufacturing, I would like to do an accurate simulation. Okay, so for this, of course, we need to change the mesh load. Okay, and the mesh can be is parameterizable. I mean, I can deal with the global. I can have local refinement, mainly based on the geometry. It can be surfaces. You can see here, I can select features. For example, I can select the valve. If I'm not able to do it there, I can expand the tree and select the valve. So no worries, it will not mesh the part of the ball which are not in the fluid. Okay, and I can say, okay, here I would like to refine the fluid cells. Okay, this is global, let's say, fluid cells. We can talk about solid cells here because we don't have to deal with conduction, so no heat transfer through the solid. And you have here the refinement of the cells which are in contact with the we can use to. What does it mean? With the Cartesian mesh, you can take a cell and divide it by 4. And one of these 4 cells, you can again split it, you can divide it, okay? Each time you do it, it's one label and so on, okay? So let's just use what we did here, okay? I'm just going to run, but just the mesh. I just want to create the mesh and check. I can do it there, or I can go here to the mesh and say create mesh. Okay. run. So it opened the same. Done. Of course, now I have overwritten the previous calculation. No results except the mesh. And if I use the SEMcut plot, so I cannot have contours, but I can have the mesh. And if we look there, it's a bit, but not enough. Okay, there is additional. If you remember, I had only one cell there, but maybe we can go further. Okay, even, I mean, here I selected the valve, I can select point, I can select whatever. If you need to refine this mesh, again, I can. What else I can select? I just selected the whole. The same results if I select the internal surface of the valve. Okay, because at the end it has used. I can push more if needed. Okay, or as well, to make the things when you cannot catch the geometry for some reason, you can deal. Let me create a new one. Insert local mesh. If you can't catch something because there is no, I want, for example, to refine the mesh in this parallelepiped, or could be a cylinder. Okay, so that I can play with this. With this. Oh, for example, around the valve here. Let me do few nanometer. And you can see here, the different, I mean, you can play with the dimension in an accurate way. And again, for example, I can say, okay, I would like to do this plus this. Okay, just as an example, I'm not thinking in accuracy, etc., etc. Again, I can try to see what's the effect of this. Let me show the results. As you can see, compare it to, as I selected the whole cylinder, I have finer cells inside the, the cylinder, plus what I did for the valve, the ball. Okay, now you can have, of course, maybe it was better to save the previous one to compare, but I think, if we run, we can have maybe a better idea. Let's, it should, you have here the number of cells. It's a small model at the end. And as you can see, the calculation is very fast, which is not the case for any type of geometry. But I remember, for example, the pressure drop was around 3,500, something like that, pascals. We may at least compare this value. If we consider that the current configuration is more accurate. So contour, maybe we don't need mesh. You have here the possibility to reset. So I don't remember exactly what was the value in the previous, but as I told you, maybe we can look to the goal, the pressure drop, if you remember, and show Okay, it's 306, 3,000, sorry, 600, and so it's different. Okay, I will believe more in this value than the previous. But again, you know, the goal was at the beginning just to get some trends when I started by default. If I need more accuracy, I have to pay attention on the mesh. Does it catch all the details? And why I have to pay attention here? Because due to the restriction to the shape of the geometry, to the sharp area, I have to catch it with the right mesh. Otherwise, the calculation could be less accurate. Like, you know, I mean, you need to represent the geometry feature with all the details as possible. Okay, this is why changing this could result in better accuracy. But again, you don't need to do this. If we compare, for example, the pressure drop 3,500 vs 3,600 or 700, okay, it's not a big difference. Okay, means I can catch the trends with the basic mesh if I have to take a decision before a design change. Okay.
So last time we started with a basic model, which is on the screen. And before starting, I remember that there was a question about template. I don't know if the attendee is connected today. Just to answer this question. So once you have defined it, let's say here we have this model. If you remember, we start with last time, and to create a template from an existing project, just go to the project here, okay, and you can see here create template, okay. Means, you know, I can give a name of this one template, I don't know, 1, 2, 3, for example, just for the and save it. Now when I will start with a new project, okay, I can, when I use new, I can select, you know, the save it template to be used with the current project, okay. Whatever if the geometry is the same or if it is new geometry, of course, as the parameter of one geometry like surfaces, where we have to set up the boundary condition, you just need to re-identify. You'll find the list here. You have to identify by editing and select the right surface to be able to complete the settings with the imported or used template. Okay. So this is just to answer this question, as I have not found last time what is the command, but the command is easy to find. It's just in the list from the project node here. You'll find, you know, the template creation. Okay. So and last time we saw this this model. If you remember, we run it. Okay. We run it. We have found some results. For example, pressure and so on. Okay. You remember we played with the mesh just because we have here a sharp, shape here, and it's better to have to refine the mesh there. Okay. And in this, as I told you, we are able to deal with configuration. Okay. And if we look to the current configuration, there is one which is the default, and there is one where there is a ball filtered. If I if I retake us tag, if we look to the details, you can see here, it's not sharpened anymore because we added a fillet. And we can see if there is a difference, okay? Should be this project, if I'm not wrong, or this project. No, okay. So, for example, I can clone the current project, okay? And I can name it the fillet, okay? We may copy results or not, so that I don't need to, is it the right configuration? Properties, okay, I don't think we are, yeah, we are not on the right one. Okay, so I have to redo the operation. Let me remove this one, delete because it used the, and this one, for example, I would like to clone it. And I should select here the configuration, and I have to select this one, okay, and validate. Okay, we have to adapt the conditions. So I don't have anything to do here, okay, because first I have cloned an existing project, and I have as well used a new configuration. And so just need to run it, okay? And we may compare results later. So run. Should be fast, huh? Because I'm using a very basic mesh. As you can see. Done. And if we look to the results, show, okay, as you can see here, we are using the filleted ball, and we may show the mesh just to compare. If you remember the last time, of course, here I have not sharpened the shape, crossing, you know. So it's better to split the cells around the shape than around the sharpened shape. Okay. We can have something, for example, just to see what's the change on this, on the results. Okay. Just to we may compare values if we want. How to do this? If we go to the result, we have a tool named compare. And as you can see, I can compare the current project to the initial project. And what I want to compare, for example, maybe we can compare the goals. The goals are, what's the, if we look here, what's the pressure at the inlet? Okay, because we know the pressure at the outlet. Okay, and just compare, and we may go to the goal plots, and we may directly, you know, I don't need, you know, to go back to this one, record or save the value. The flow simulation is able to read what he needs and compare. So you can see here with fillet, without fillet, what is the pressure drop? What is the pressure at the inlet, sorry, okay? And of course, you have to compare apple to apple with the same conditions, okay? I'm not sure, I think we have the same condition. So it's a very basic, okay? As well, we may compare through the results. We may compare not only values, okay? But maybe we may compare the, if we have the same list, for example, the second cut plot. I can compare this one to this one, ask, you know, do compare, it work, and it create the pictures. So we can see that, you know, with the same scale, we have two different, mainly around, you know, the valve inlet, the ball inlet, sorry, okay? As well, here we are comparing original to unoriginal. You may compare a difference. What is exactly the difference between the two? Where is, we can merge in one picture both of minimum, both of maximum, which could help, you know, to find the maximum of several configuration in one image, in one shot. So now let's, before leaving this example, okay, I want to play with another configuration. Let me close this one. We may save it. And I have created another model where I extended the pipe, okay? And I have played, let me show you something. I want to play with the angle, okay? In the configuration, if we go to the groups, you know, it was 165, and now it is 155, okay? In the original, it was 165. Sorry. And I would like to, why I have to do this? Because if you remember, if I want to get good results at the outlet, it was still disturbed by the flow. There is a recirculation, etc. If I want to, for example, measure a good pressure drop, I have to extend the pipe, sorry, and make the measurement there. When I have a stable flow, okay? So using the same condition, I don't remember if I need to run it. Which is not this one. Okay, so let me. Okay, the domain is good, so everything is good. If I run with new mesh, new calculation, oh, looks like there is a problem. Is it closed? So what I can do? The clone maybe didn't work very good. The mesh is okay. So there is a tool where we can check the geometry. Okay, there is a problem. We should find the positive volume. So means there is okay, I know what to do. Looks like there is a small
Sorry, guys. So I hope that, that it's passed now. Okay, I was trying to, so it's nice to have to encounter a problem here, but maybe I can go back to the check geometry. Again, without this pre-processing, there is no free domain. I tried to do this, and looks like there is something. We may show the volume fluid. Looks good, which help you to to check that everything was recognized. And then here looks like, so this one is okay. This one is okay. Okay, no problem. I don't understand why we cannot run it. Even if I have, maybe I should use the Boolean, the mesh Boolean to make sure it can solve new calculation mesh. Looks better. No. There is still a problem. Okay. So maybe I have some leak somewhere. Okay, so I just created on on fly before the session. So I will spend more time on it, and maybe I can send you some picture. But again, here, if we look to the previous results without the extension, okay, and load. Let me just show this one. We can see here. Let's switch to the velocity. Okay, you can see here that at the outlet it is not very stable. Okay, and we may look as well to the vectors. Okay, so you can see that maybe due to the circulation, if I zoom here, at the outlet you have a part of the surface which results in inlet, okay, which is supposed to have the full. It's due to the circulation. This is why I extended. Okay, so it will fix the problem because the outlet will be far of this area. This is the idea. Sorry if the model doesn't work as I expected. Okay. My next example, and as I told you in the example list, okay, you may find different lessons, different example, and I selected the heat exchanger, okay, and I will find a way to share with Prasad all these file, and if you have access to Flow Simulation, you can play with, okay. So this is a heat exchanger, okay. If we look to the section of this one, okay, you can see here that you have two domains, okay, the fluid domain inside the blue and the fluid domain inside the pipe, which is horizontal. What's the goal of this? A heat exchanger, usually you have a hot liquid and a cold liquid, and you try to cool or to heat from one to the other. Okay, for example, here, let's say I want to cool the liquid crossing this pipe by a cold one, okay? And to do this, so the model, the geometry is very simple here. It's a simple heat exchanger The real heat exchanger and the industrial one, more or less, it's based on the same idea here, except you may have hundreds of pipes crossing the main cylinder, okay, to extend the surface of exchange between the hot and the cold liquid. And sometimes there are some additional baffle, to create the stagnation, to spend more time with the cold liquid and get better chance to enhance the cooling. But let's stay simple, okay? So here, what do we need to do? Okay, if I start from a new one, okay, and we'll see later the existing. So as we saw last week, let's name it demo. And here it's flow simulation configuration. It's not a SolidWorks configuration. For the moment, we have only one. And I don't know, for example, I told you last week, for example, we can play with some, using SI system, but for example, I would like to play with Celsius degree, okay? And maybe, I don't know, some additional. Next, to deal with heat exchanger, I need to have conduction through the solids, okay? Because of course, the T fluid here, the two fluids are not in contact, and they can have heat exchange between them through the conduction of the solids. I just need to check this one, okay? Then we can say, do I want to have a time-dependent solution to see how long it takes to get, such to reach a given temperature and so on. So, but let's stay simple. It's an internal one, okay? Next, I would like to play with liquids, okay? And for this, I need to select maybe water for bath. So I don't, you can have two liquids if you want, if they are different. For example, I would like to cool with water another type of fluid. And in this case, you can select another one. Let's do this, which is not the goal of, but just to have an example of two. There is no, we are not going to mix them. Okay, let's say, for example, the second liquid is ethanol. Okay, and next, as I have checked the conduction through solids, I need to select what is the main material. Could be different material that I can assign later, or maybe it's the same. Okay, could be aluminum, for example, from the list. Next, we may deal with the roughness. Okay, and next, what is the initial temperature? We can deal with this and finish. Okay, so we may say as well that the problem is symmetric. Okay, on the YZ plane. Means, if I want to save time, I can see that I have min max on X, min max on Y, min max on Z. And you can see that maybe X equals 0 could be a symmetry plane. Okay, this side or the other side. This one is symmetry. Okay, doesn't matter which side you select. So I can save mesh, especially if you have a very complex geometry. Okay. And what next? Next is now to define the conditions, of course. So usually when you have a heat exchanger, the inlet of, for example, this pipe is opposite to the inlet of this one, just to have opposite direction. That's what's usually okay. Let's maybe start the condition here with this face, and let's say it could be a mass flow, not a problem. I can say 0.01, for example, kilogram per second, and I can deal with the temperature. It's the hot one, for example. Let's say it's a 300, okay? And of course, as I have selected two liquids, I can say here it would be 0 mass fraction of water and 100% of ethanol here. That's it. It's very easy. And there is no mixture here. So it means here I will have only the, and that's it. I told you last week as well that I can directly create goals on this inlet, and you have the appropriate one. For example, I can say, I would like to get the pressure, I would like to get velocity, and so on. Validate. You can see the symbols there. You can see the creation of this condition, and as well creation of two goals, so that I can follow the value of what I have defined here, pressure and velocity. And here I can directly select the face, and you can see here create a boundary condition somewhere, which insert boundary condition, pressure environment. So it's a shortcut. Okay, it's a shortcut. I retrieve it here if I want to edit and modify something. So I don't know what is the temperature. It will be calculated by the software because it is the outlet. Okay, I don't need to play with this because automatically it should be calculated as well. I don't need to this one, but I can define what's the mass flow rate there, just to check that the inlet and outlet mass flow rate are the same. Okay, of course velocity if I need, but that's it. Now I'm going to see with the second fluid, which is the water. Again, I can select and use, it's very flexible. If you want to use the contextual menu, or let's say here again, it's a mass flow, let's say 2.5. Okay, as I have more, it should be at the cold fluid. Let's use the ambient. Okay, and here it's 100% of water. Okay, and again I can say, as I have defined it, mass flow, I can select pressure and velocity as gold. Okay, and the last one is this phase, where I have to select which type of condition. It's environment pressure, and I don't need, so maybe the goal to make sure that the mass flow rate, the conservation of the mass flow rate can be, and as well velocity, for example, why not? So automatically I have set conditions and goal. And we saw last week as well, we can deal with equation if you want to get a given scalar value of something. Just use a formula and you get it. Okay. Then we need to run. As I want to deal with fast calculation, I'm going to use, the default
global mesh. Okay, I have not changed anything. Let's run it. There is no fluid volume in the project. What we need? Is it because of this? So the symmetry doesn't work on this one, but it should. Solver has finished, as you can see. And now we can see some results. Let's create some maybe not this, maybe this plane. Yes. And let's see for example, temperature. Okay. So here, as you remember, we have the inlet at 300. Okay. For the current plot, I'm using this is the global and this is the local maximum as well here. Okay. You can see here a sort of gradient. Keep in mind, the inlet of the hot fluid is there. The inlet of the cold fluid is there. So there is more exchange in this area, okay, than in this area. And there is even in the solid, we can see as well here, it's global temperature. We can see only the temperature of the fluid. Tac, tac. We can see only the temperature of the solids. And it gives you an idea about the different heat transfer exchange. Okay. So this is just to deal with with the given conditions. Okay. If I look to the in the goals, I can select all of them and show a table. So here you have directly the different value of pressure at the first inlet, pressure at the second inlet, and so on. Okay. And as well, maybe I missed an important goal is the temperature of the fluid in average or something like this. But anyway, we can do some calculation here. You can have, for example, select a section somewhere and define, for example, some additional, can have surface parameter where you can select a surface, or you can select different entities, for example, the current plane, okay? And I can have a global temperature of the fluid here, and you have here an average temperature of the fluid in this one, okay? So this is just an example how to set it. Now I have two calculation where the symmetry is there. I don't know why mine didn't work. Where I have results, if I'm not wrong, and we may compare what we did. What did you here show? Maybe I can hide the mesh where we have velocities and temperature of the fluid. Okay, and as well, let me hide this one. Show this one where we have Oh, it's the same. This one is, and this one are, yes, it combine, how to say, two velocity, yes. This one include, we can see the temperature of the solids. This one, it's opposite, I mean, it's perpendicular and show on the side. Let me maybe hide this one. And you can have, here temperature distribution inside the two pipes. Okay. Whatever. Okay. Here, if you remember, I tried to show the results we may combine with mesh. And you can see, let's say it's a very basic mesh. Okay. Sometimes you remember that I I explained you the idea of having partial cells. Here, the cells which are shared, for example, this cell has a part of cell is pure fluid and the part is pure solid. Okay, so the calculation is done with one cell and we will have temperature of the solid, temperature of the fluid. Okay, if I take only fluid temperature, you may understand better. Okay, then I can hide the geometry just to, so you can see here it's the place of the solid when it is grayed, like here and here. Okay, and we show results only on the fluid currently. So, and you can see you have several partial cells. Now, for accuracy, maybe I need to refine the mesh. Okay, so here it used a level 3, and we cloned the configuration and we use here level 3, level 5. Okay, so it's because the geometry is hidden, display geometry. Okay, and we did a calculation. And let me show this one with the mesh. You can see that the mesh is a bit smaller, okay, a bit refined, but it's global. Of course, we can do like we saw last week. We can have, I mean, if I have to validate this, what I will do, I will try to refine the mesh on the walls, because the exchange will be calculated on this area. Okay, so means if I want to catch a good gradient of the temperature from solid to fluid, I can measure this. And if you remember last week with the ball valve, I tried to show that we can create a local refinement by selecting a part, for example, the pipe. Okay, and I can say that here I would like to refine in this domain the fluid. I would like to refine the solid cells, and I want to refine cells at fluid solid boundary, and you'll get better refined mesh. Okay, so it just some tips if you need to have accuracy and validate a project. Now, as I told you, let me maybe just keep this one without the mesh, and it is global temperature. As I told you, we have this tool name it compare. And maybe I'm interested to compare level 3 and level 5 in terms of goal. What are the goal here? The goal is a global, it's a volume goal of the tube, okay? And uh, it's based on the temperature. The goal is the temperature. Let's compare them. And you can see in one case, level 5, I have a global temperature of 339 vs 341. So there is more or less 1-2 degree difference, okay? But I can consider that this one maybe is more accurate, okay? So the first one is to get the trends. If you have to deal with design change and so on, we may get the trends by dealing with the a fast calculation, so using level 3, okay? And for validation, maybe you can spend more time just by dealing with the refinement, okay, of the mesh to get better accuracy, okay? There is a question, looks like. Maybe several questions. Should I ask? Should I read one of the question? I ask this because many times the hardest part of a project is troubleshooting the potential error. Not sure, the geometry recognition is very powerful with flow simulation and with the check tool, etc. Of course, if you have some CAD errors or some gaps or leaks, clearance, yeah, it could make the thing complicated, but you have some SolidWorks tool to repair before going to flow simulation. If condensation were to be formed, is there a way of calculation the condensate that formed? So we are able to calculate humidity with water vapor and so on, okay, to follow condensation. Yes, we can. It's limited, okay, but you can calculate this. And I can see a question when looking at the goals. Is there maximum the value that was seen during the time the solver is running or at the end of the solution? If I go back to a goal, as I have some goal here, you have here the current value at the end, but you have the average, the mean, and the max, okay? And of course, you may get the history during the calculation before it converges, it cross some min and max values. That's maybe I can now switch to another one, which involve heat transfer, but in a different application. Which is this one. Okay, it reminds me you maybe the electronics cooling. Okay. So with flow simulation, we have two options. In addition to the standalone, which is the main module, we can have access to electronics cooling and to a module named HVAC, HVAC, which are optional modules, but giving you an access to some advanced feature. Okay. So, of course, on my side, it is installed and it can allow me for additional things. Okay. So, as you can see now, here we have PCB. We have 3 PCBs. Okay. We have an enclosure, and we have some component, let's say the main chipset, some capacitors, and we have on these two PCBs some additional chips. Okay. As well, here we have let's say the power. Okay, it's a simple model. It's a simple problem, but with flow simulation we are able to do this. So it will take time, to do it step by step, but there are some workflow who can help you to do this. Let me create a new one and we'll back to the current configuration. Okay. Let me name it demo. Use SI. Okay. I think here again I would like to deal with Celsius and so on. Next. Of course, I would like to deal with conduction in the solid. Otherwise, I will not take into account the heat dissipation inside the component and so on. It's an internal one. Okay. Sorry. Next. Usually, I just have the air as the fluid, the gas here. Okay. I don't need that. Usually, this is what used for electronics cooling. Okay. And the rest, by more or less by default, except I have to use here. I know that they have maybe 5 groups of material: the enclosure, the different chips, the different components, etc. So here, I'm just going to select the default one. Okay. And for the other, I need to specify which material it is. Okay. For example, here I can say, okay, the enclosure is made with the aluminum, something like this. That's it. And just need to provide some default values at initial value, for example, ambient temperature, and finished. Of course, here it works. Why it works? Because if we look to this enclosure, we have added some leads, like here, which is the place of the ventilator, of a fan, sorry. And on the other side, as you can see, we have some leads here. Okay. This one, and as well on this side. Okay. Here there are not leads, but the screw holes where I added leads, so we don't need to have specific condition here. Okay. And we may assign them insulator to not affect the global calculation. We don't need conduction through this. As well for the lead, this one, which is the fan location. Okay. And this one, this group. Okay. So this is why I have a closed model. Okay. And at any time, when you start, it's good to deal with check geometry. Okay. First of all, I want to make sure that, processor, check. I'm surprised because normally it's closed. It is internal, exclude cavity with that condition, okay. Okay. I'm surprised. Because I was able to calculate, sorry, what I did. General setting, tac, internal, CAD boolean, or we can deal with this, it's not a problem. It helps to correct if there is a problem in the geometry. I have not defined it. I understand. I'm sorry. I'm sorry. When you start, you do not have any condition. Let me back to the default, to not believe that because I did this. So by default, it was CAD boolean. Okay. And when you do check geometry, here it's closed, and I have not defined any condition. And there is an option exclude cavity without condition, because sometimes you can have, internal volume that you don't want to take into account. I have to uncheck this, and here it's better. I was surprised, because normally, and if you look to this, you may check the fluid volume. Okay, so maybe here it's difficult to see inside. If you want to check this one, okay, you may ask to create fluid volume, okay, and deal with check geometry. It will create the fluid volume and open the SolidWorks part. Now I'm able to see inside and get an idea about the fluid domain, okay, and make sure that it respects the shape inside the enclosure, okay. So it's very nice to have this tool. Okay, I know that there is a bug here. I just need to refresh. Okay. Okay, so we have defined the general settings, okay. Now I have to, maybe you are not going to define all things step by step. I will switch later to this one, but just to give you an idea. Here, I need to, for example, to select all these are chips, for example, and select from where some different material, or use some user defined. Okay, for example, here I can see if I have different material that I can select. Okay, and of course, at any time you can browse your engineering database and see different type of material. For example, for printed circuit board, we have some predefined material, okay, or user defined when exist, and so on. As well, in the if you have some specific component like 2 resistor component, of course we have some predefined from the electronic industry, and you have this library if you have the electronic cooling module, okay, or user defined as well. And from material list, okay, I can go to the solids and select the appropriate one from predefined, okay, like we saw, alloy, blah, 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 and from user defined, like we saw, and so on, okay. Sorry. For example, for the current one, I can have the PCB, okay, and use it because already save it, okay. So means here I should define. So for the enclosure, it is the default one, but I should define material for this group of chips, this group of capacitor, and the material for the main chip as well. I need to define material for the power box, and as well for the heat here for the heat sink, which is mainly aluminum in general. Sorry. And as I told you, I have 3 PCBs that I have to assign PCB material. Okay. Let's assume we have defined it, because we can browse these material list later in the defined project. Okay. Then in the boundary condition, we can have, of course, on these surfaces. So like I showed you last week, you can select by select order when you sorry, that set boundary condition. When I use select boundary condition, I have select order in addition, and you can see what is the order. The order is the inlet phase, the internal phase. And now, like I'm preferring, when it's possible, to use section. This one should be okay, and I'm able now to select this one, and this one. Oh, sorry, I missed the shift button. Boundary condition, usually there it is a pressure condition because it's outlet. That's it. And now maybe I need to have this one on the other side. Oh, yes, and I want to, yes, this one should be okay. I can select this face from this side, and I can define a fan. For this, I need to go through different conditions which are not there. Okay. If you can't find them here, even in the condition, just you have tool, where it is, insert, tool insert, normally click breaking, copy to project, create copy to parameter, where it is, insert, sorry, insert, I should have fun, where is the fun? What happens there? Because looks like it showed me the results. Let me do it in another way. Tools, somewhere there. Insert, no, it's not so. Insert, tools, file, SolidWorks application. Oh, I can find my tools. So flow simulation is still there, okay. Simulation, okay. Simulation, study, I should find. No, this one is for structural only. Oh, where I can find my flow simulation menu. Yeah, okay, it's not there. It's not there. Because here I can't. I can, of course, here I can find, or maybe if I select this and insert fan, I can find it here. It's external inlet fan. And I can here, of course, select from the list a fan, and that's it. You don't need specific condition. Okay, it's an inlet, it's external fan, but an inlet. And of course here, the surface, we remove the center, which would be the hub of the fan. Okay, but I should be able to get the menu somewhere, and I'm surprised to not find it directly, because usually, but it's there. Flow simulation, insert, sorry, and you have, because by default, you don't have on the tree all the condition. When it is not there, you go to insert and select what you will need. Okay. And the fan should be there. Okay. So in terms of flow, I have enough. Okay. Now I need to define additional things. Let's assume I have defined it PCB, blah, blah, blah. Okay, okay. But each component could have, for example, this one, it could be a heat source. Okay. Again, for this, I need a specific condition. Okay. And if I'm not able to find the right here from the list, the right condition, again, I should, where it was, again, where it is flow simulation, there, insert, somewhere I need to find a volume source, there. Okay, select the chip. It's a solid, so it select the surface, and it select the part. And you can say here I have 5 watt. That's it. And you have to do the same for the different chips and the different component. And that's it. And you do the calculation. Now, if I switch to the defined one, let's bruise what we did. As I told you, except for the enclosure, if we go back to the general settings, the solids, okay, we have stainless steel for the enclosure. Why? Here you don't attribute to it, but it's the default one. When it is not defined, it uses this steel stainless. Okay. How about the other PCBs? PCBs, we use a material defined in the, we can edit it, of course. So PCB has some specific, so here we consider it's isotropic, but it can be multi-layer. Okay, in this case, I have additional, but here we are using, let's say, a simple case where we need to deal with the density, with the specific heat, the conductivity, okay, the thermal conductivity, if the electric or not, and so on. Okay, this is for the PCB chips. Created it just to. So these are component. I mean, all the small component which are there in blue. Density, specific heat, thermal conductivity, and so on. Okay. As a formation, we have melting temperature. In case during the calculation it reaches this temperature, you will get a warning message. Okay, and so on. Heat sink. This one. It should be aluminum. That's it. We don't need to define additional thing. What else? The leads we created, we just assign them insulator, okay, to not affect the results. That's it for the material. Then for the condition, just the environment pressure on this outlet and the fan. Okay, it's from the library PAPST that we have in the engineering database. Okay, just we need to select the right one, and that's it. If we look, why we don't need to let me edit, and you can edit any fan you can find. Okay, the 412 that we are using, whatever where it is, this one where it is, 412. 333 33 412 is there. So a fan, sorry, is defined by rotation, dimensions, etc., etc. But the most important data is the curve here, where we have flow rate vs pressure. Okay, and function of this, the condition will be well defined. I don't need to have a condition like mass flow rate or velocity and so on. Just define the fan, and that's it. Okay. Okay. And as I told you, we need for the main chip, if we look, we have 5 watt here. And for the capacitor, we just define temperature. For the small chips, 4 watt for all. Okay. There is, if I'm not wrong, no, it's okay. Yeah, it's this one. And the power, which is a box, but here we just define the temperature. These are the conditions. Okay, there is a question that I will answer just later. Let's continue on this. What's the goal of electronic box, electronic enclosure like this one? Is to make sure that all the components are not over a given temperature, okay? Because there is a maximum temperature to be supported, otherwise the component doesn't work. Are we sure that the flow inside the enclosure is has a good distribution, and so on? So I already ran this one with a basic mesh like we have in this example. Okay, it's only 3, and we have some the minimum gap size to be taken into account here. It depends on your geometry, but in case you have, so that the mesh will adapt to this value. Okay, because sometimes, for example, I don't know, you have a small space between the 2 solids, so that it will be considered for the mesh. So I already ran this one. Just for information, So it needs 148 cells. Okay. The CPU time for this is not long. It's not so large. 211 seconds. Okay. To converge, to get convergence. Okay. Means a few minutes at the end. 5 minutes, something like that, if I'm not wrong. Now, what I can get from the simulation, if I go to this result, which is the velocity on the cut, it's a cut plot of velocity. So you can get an idea. Of course, maximum is at the fan outlet. Okay. So again, my condition are pressure here and the fan, inlet fan, external fan, sorry, with inlet conditions via the enclosure. So you get here an idea. So just from this result, I can say, okay, it's good to have the fan in front of the heatsink so that I will get a better cooling of this component, which is the main chip. Okay, let me continue. Let me hide this one, of course. Here we have the fluid temperature with combined with the vector plot. So again, okay, it's just, I think I'm going to mute someone. How I can do it? I think we are okay now. Okay. What's next? Let me hide this one. So just with this cut plot, I'm able to see something, the quality of this, should I change something or not? Okay. So of course, I'm as well interested by some other values, surface plot, for example. I can select the ships, okay, and get temperature of this. So you can see here, let me check that I'm showing the maximum for each one. Okay, and have a look on this. So for example, here I have 33 degrees C. This ship has less than 33 for sure. Okay, and if I use the maximum, the global, even though, okay, I can get this result. Now, at any time, of course, for example, I can hide the box, the enclosure, so that I'm able to catch something. And you remember this tool? Sorry, this one. I can probe the results. Okay. It's a sensor for what I have. Okay. Of course, maybe I can hide the chip, the heatsink, sorry, and I can probe my results on it. Okay, I'm sure that the main chip is not too hot. Okay. So what I have hidden, which one is the what is the enclosure there? The heatsink. Okay. Now as well, I can have different, where are my second surface? Let me hide this one, show this one, which is specific to the power, okay, and to the capacitor. And with the props tool, you can get, you know, the temperature of this. So if you are satisfied with that, means that it's well cooled and so on, and it's fine. It's nice, sorry, to show the trajectory that we can animate, and you may zoom and see if all the area are well ventilated, let's say. Okay, of course, the main component is the ship, and we have to make sure it is well cooled. Okay, as well this one, the power, and looks like there is a small flow here, smaller, but there is something. Okay, of course we may maybe add another ventilator if needed here or not. So it gives you some information that you can you know, use to modify the design if needed. So we have defined some goals. Of course, we can edit, select all of them, and show, which are pressure, okay, at the fan surface, which are the temperature of the fluid, okay, which are as well the inlet static pressure, and we have which is more or less the same value than slightly, and the mass flow rate, the temperature of maximum temperature of ships, and the small and the main one. Okay, so with this, you can make sure that you are in or out of the you know, of the standard concerning the electronics cooling. Okay. So is there any additional question? I know there is one question that I need to answer. Okay. At the meantime, you may ask some additional question. There is a question: would you be able to share resource where CAD, mesh, and pre-processor Boolean options should be used, or how these options affect the solver? So there is two things, let's say. The flow simulation can use the CAD Boolean operation from SolidWorks. So as you know, it is integrated. Flow simulation is integrated in SolidWorks. Okay. Now it can use when it detects or extracts the fluid domain, it needs to do a Boolean operation. So it can use SolidWorks operation, or it can use, this is why, sorry, up. This is why you can, sorry, here, by default is CAD Boolean. CAD Boolean means we use SolidWorks. But sometimes, you know, you can have some small gaps, especially when you import a file, a complex file, okay? And you don't know how to correct it. Just in this case, use this is from flow simulation side, okay? Means here, if I select this one, oh, if I select this one, I will ignore the CAD Boolean from SolidWorks. And it use its own, which is, let's say, with a mesh philosophy, a mesh point of view, it can automatically ignore some gaps, default, or or some overlapping or something like this. And there is another tool which can go with very dirty geometry, very with a poor quality, and especially when you have a, you can use what they are naming mesh boolean, which try it doesn't work 100% of cases. The mesh boolean will try to mesh the complex part and deal on the mesh to merge and do boolean operation. Okay, so but let's say mainly you may use by default the cat boolean, or this one if you have some issue with the cat boolean. If it doesn't work, you need to back to SolidWorks and, for example, use where it is, if I'm not wrong, it's not under evaluate, maybe, yeah, you can use interference detection, clearance verification, and do the needful. Okay, now as well you have a tool here to track if there is so maybe I need to do a section, this one or the other side, not a problem. Let's say I'm not sure 100% my geometry is closed. Okay, for this case, you can go to the lead tracking, select, for example, the internal face of the enclosure and the external face of the enclosure. Okay, and try to find if there is no connection, like here, means it's closed. I mean, a particle who goes from the internal face try to reach the external face, no way. If there is, you'll find colored, sorry, you'll find the leaks colored by different colors. Maybe let me create a configuration. So for the moment, this configuration, there is no fluid project, flow simulation project. And for example, let's say I would like to remove something like okay, let's say maybe the small holes. If you remember, there are 4 holes here. Let me suppress them. Okay, means here I have I ignore them if I'm not wrong. I ignore one of them. And let's do the same by ticking the other side, maybe. And go to leaks and try, for example, to say this side, the internal, this side, the external. No, sorry. This side, the external. And okay, so there is something. And you can see that there is a leak here between this face and this face. Okay, which involve these are 3 faces. Okay, the internal one, the whole face, and the so I think it can help. It can help to to identify if you have any specific problem. Okay, so with flow simulation, of course, you don't have magic tools for everything. but you know, it could help you to solve most of the problems you can face when you have a complex assembly. So maybe the last model I want to show you today is the porous media. Okay, what is a porous media? So let's say we have seen an example of the ball valve just for pressure drop. We have seen the heat exchanger, okay, and the electronic cooling, which both of them involve conjugate heat transfer, conjugate, name it CHT, between the fluid and solids, okay? And now I would like to talk about this exhauster, where we have what we are naming porous media. Let me take this one. Usually in a exhauster, you have a sort of cartridge, okay? Usually you have different aspects. Could be a sort of honeycomb shape or something with a lot of holes, okay? The idea is to, of course, to catch from between inlet and outlet, to catch, you know, for example, some molecules as well. It could change the pressure at the outlet to have lower pressure, etc., etc. For this, we cannot mesh the real shape of the porous media. Okay. If I can find an example. For example, if the structure is something like this, okay, it's impossible to mesh, and there are several possibilities, you know, for when you have a filter. Could be something like lattice design, could be some holes, and so on. And as you have, let's say, very small dimension, it's impossible to mesh. Okay, you'll waste your time by trying to mesh, because, you know, just to take into account the pressure drop through this porous media, etc., etc. So by replacing by a volume like here, okay, so the idea is to have the external shape of the porous media, like you can see there, and assign a specific material. Okay, so all other conditions are similar. Okay, as you can see in orange, you have the exhauster. We have defined lids for inlet and outlet. Okay, as you can see, we have here a velocity which is at 10 meters per second, which is not a low velocity, and the outlet is, let's say, the environment. Now we have defined it for these two porous media. First of all, if we look to the SolidWorks assembly, we have the housing, we have the two lids, and as well we have the two monoliths, which are the let's say the exhauster cartridge. So if we look to the shape by opening this part, it's a solid. It's a solid one. Okay. But of course, there is no details. There is no details about the real shape of the porous media. Okay, like there. And of course, if I need to do an additional things, okay, which is let's say where it is. Yeah, if you don't define, I mean, if I suppress the porous media for this, then I will have 1, 2, 3 fluid domain, means there is no communication between the inlet and the outlet. And the porous media will automatically, it's a sort of liquid and solid, okay? And the main data for this, let's say we can have isotropic, means the flow inside the porous media can go in any direction, okay? And I can have orthotropic, means I have the main direction, okay, or two directions. So, and this is one of the parameter to define the porous media data. There is what we are naming the porosity. The porosity is the rate between, it's a sort of resistivity, let's say, okay? And where it is there. So you can deal with mass flow rate, or you can deal with volume flow rate, okay? And just with this value, and this is the value of the sample tested, of course. You know, it is not something that you can guess. When you have porous media, you have to test it so that you don't need to have the real model of the porous media to use it in simulation. Okay, so the sample, this is his length, and the surface which represent this this sample, and that's it. Okay, and you can have different. If I go to predefined, for example, for filter, for let me up. I can have different value or different way to represent this, and you have some table for each one, even my current, of course. This is the flow rate versus the pressure. Okay, higher we can see, you can say higher is the pressure, higher is the flow rate, and inversely. Okay, so this one is linear. If I go to this one, you know, have a specific pressure velocity. This one is velocity, and because you can select here which type of which type you want to use. If I go to this type of filter, and polyester filter, and so on. And of course, if I look to the properties, isotropic, but it can be only, you know, it can be different. Okay, in this case, you have to define in two direction in case. Okay, that's more or less how to define the porous media. And just, you know, by selecting a porous media means, you know, the fluid domain is from there to there. And that's it. That's it. Okay. Then after defining the velocity and the pressure drop, okay, here we can, by defining two goals, which are the pressure at the inlet, the total pressure at the outlet, and if you remember, we can have an equation here, which is the difference of total pressure at the outlet minus the total pressure at the inlet, which provide you the pressure drop through this this porous media. I think here we have the basic mesh, means we can run it in a few seconds. By the way, while it is calculating, you can deal with heat transfer inside the porous media if needed. Okay. Let's look to the results. So here it shows the pressure, and as you can see, when crossing, it's not necessarily uniform. Okay, you can have, of course, after, yes, okay, but it's because of the velocity direction there. Okay, but at the outlet it is mainly a uniform. If I show the two square showing the porous media. Okay, so that's a sample result show you if how it works, but I think the most important results will be the pressure drop, okay, which is done by this value, as you can see, which is the difference between these two pressures. So it's a small value, but keep in mind we are dealing with gas, okay, so it's not so small. For liquid, yes, but for gas, it's a real pressure drop. So that's more or less, you know, the results we can extract. We may be curious to see how the trajectory are, okay, and maybe I can play with the dimension. Yes, okay, just to have a better view, okay. And if we play with, we can say, yeah, a part of the first porous media is there is nothing. I mean, low velocity or low exchange because of the orientation of this, of course. This is another subject, of course. And sometimes it is interesting to say, I have main direction, means there is no flow in X direction for this case, only on Z direction. You can see here the which can you know, drive the flow in one direction only. Okay, so this is something that you can define in the properties of the porous media. Okay. By the way, you may know that we have a solution on the platform which is named Fluid Dynamics Engineer, okay, which is of course more advanced in terms of CPU, etc., because it's a cloud-based solution, okay, with an option on-premise, means you can have embedded with the package up to 16 cores on your local machine, as well on the cloud, okay. And if you need more, of course, you may ask to access up to 144 cores on the platform, okay. For this is, let's say, if you have a ball valve like we saw here in this session, of course, it doesn't require this solution, okay. Now, of course, I tried during this these two sessions to show some basic model, because Of course, it's a learning path, more or less. Okay, but we can have some very complex system that we can solve with flow simulation, by the way, but as well. And flow simulation is a desktop solution, means you need to have a local calculation. And sometimes, for example, if you have to deal with a complex geometry, plus you need to deal with transient calculation, sometimes you need a week on a workstation, okay? vs a few hours on the platform, because using cloud computation. So keep in mind that, of course, we may solve similar problems, but sometimes it's there are more benefits to use the platform, and it's connected to SolidWorks. Not exactly in the way we saw with flow simulation, because flow simulation has the benefit to be in the same UI, because at any time you switch between SolidWorks and flow simulation, okay? With the platform solution, let's say it uses what we are naming the connector, means I can save, I'm not logged now, but I can save my current geometry on the platform, use for CFD or structural. And if I need to, I can save revision A. And if I have to deal with design change, I can save revision B, use the same settings on the new geometry and run, so that I'm able to deal with what if analysis, okay, and so on. Okay, in a few words, of course, it's so here, just to give you, for example, we start with SolidWorks with a heat exchanger. As I told you, we can have a very complex heat exchanger that you can see here, where I have hundreds of pipes. Okay, it's similar to the sample example we saw. Okay, and we may try to find how many revolution, because here we have some baffle to optimize, the performance. Okay, and then, as I told you, you are in SolidWorks. You switch to the platform. You retrieve your geometry. You define by this interface your settings. Okay, I try to go faster. Okay, and then once you run it, this example has maybe 15 million of cells. Okay, it uses body fitted mesh, hexa mesh dominant. Okay, and as I told you, using, as you can see here, you can use cloud computation, and you get results. You may use credits or tokens for cloud computation, and then you post results. You can get curves, different values, and so on. And you may back, as I told you, to SolidWorks. You change it something, okay, and you can compare different revision, different configuration, and then you may see the efficiency and decide which one is the best one you want to use. Okay, so it's just an overview of a complex model that we can run on the platform.